Hello there and welcome back. In our last video, if you have not seen it, I'll be putting the link on the top right here. We build this lexer, and the lexer was able to convert our string input from the user and generate actually a vector of tokens. So these tokens were either numbers, strings, identifiers, or even some literals like null, booleans, true and false, as well as we also were able to implement the brackets in terms of trying to show precedence in operation. So this is what we had in our last output, and in today's video we should be able to convert this into an abstract syntax tree. So without wasting so much time, let's now get back into our CMake file, and I will be adding here some new files which you already have them here. So first and foremost, I will add the AST. We'll do the front end, then we'll do the AST.cpp. Another file I need to add here is the parser. I'll do the parser.cpp. So we'll be using the AST to kind of have structures on how our AST should look like, and we'll be using the parser to kind of take the stream of vector of tokens or vector of token and then convert it now into AST, and then generate AST and pass it back. So the AST is what we'll now be using to pass into maybe our interpreter in our next video, whereby we'll now be able to evaluate our stream of input tokens into output values that we can actually work with. So in terms of working with the CMake file here, that's all we'll be doing for this class. I'll come back to the main, the CPP here, and inside here, let me include the two files as well. I will do include expression evaluator front end. Let me do parser. At the same time also I will include I think I have a typo here, so let me just fix that quick. Expression evaluator front end and do AST. Good. I think that's good for this class. So I will change this part now and I will convert it to parser. I'll be showing you why shortly. And then in this one, let me comment out this for now, and I'll be showing you why. So let's save this file. I'll come to our parser. So we have our parser.cpp. Let me just get the parser.h first here. Let's add the include if not defined. Let's do parser. Let's define. So you can also use pragma ones depending on the compiler you're working with, but I think most nowadays both are actually supported, so whichever you prefer. So let's add a class called parser here, and similar to our lexer class, in our public accessors, then I will create a constructor here, but I will just make it to be okay. Let's just for now do default. So the compiler will generate as 1, and then for our parse as well, we need to have a method called parse, and parse should take a const reference to the user's string input, and then in our private methods down here, members here. Similar to our lexer, we'll be having similar methods as well, because we need to iterate over the tokens that we have. So we'll be returning a token if we call pick. We'll be returning a token if we call advance. We'll be having void. Let's start first with the boolean, and for the bool type it will be end of file. Also we'll be having a void called expect, and for this expect it will be taking token type. Let's call it T, and then a const reference to a standard string error. That way. So this is similar to what you already have within the lexer, but now it will not be working on characters, it will now be working on the tokens themselves. Then down here we'll have lexer. Let's create our lexer here, and then in our lexer, let me add a new method. Let me add a new method in our public here. It will be same to this. It will be same to this. So it will just return a of token, and I'll just call it tokens. So let me implement it inside the lexer. After tokenize, I will just put that method here. And I will just call it similar to that. So we'll just return m tokens. Good. So that should be it. So in our lexer class, I think we also need our cursor. Initialize it to 0, and then all these methods need to be implemented. So let's go to parser.cpp. So first and foremost, let's include our parser header file. I think we need to go 2 folders up, and then includes expression evaluator, front end. Let's call it parser. At the same time, we also need to include the token. No need to, we should just include it. No, we can include it here. Okay. So let's include the lexer here. Reason being, we'll need to access the token type and the token stuff. So So for most of these methods, we know how to do them. So let me just implement them quick and then we'll continue. What you've been able to do so far is for pick, we're basically returning the token at the current cursor index value. For advanced, same to pick, but you also later we increment the cursor value. For EOF, we are just basically checking if the current cursor value is greater or equal to the token size. And tokens is the method we've just added to the lexer to return a constref to the vector of tokens which is in that class. And then for the expect method, instead of comparing it to character values, you're comparing to token type. And we'll be getting the current token and then checking the type and comparing it to what you've passed in. Similar to the before, we'll be also having this not end of file. And then you advance, of course, we return down here. You also need to throw an error, and this will be error that. Okay, we'll fix that slowly as we go on. So before we implement the pass method, we need to now implement AST, because pass will be generating AST as we walk through each and every block of it. So to generate AST, let's go now to AST first. So let me first save this contents. Go to ast.h. This is the include guard for AST. And in our AST, we'll be doing similar to what we did in our lexer, but now it will be having a slightly different kind of thingy. So in our AST, we are trying to build the structural representation. So here we're no longer dealing so much with tokens, but we're dealing with blocks that encompasses the tokens. So a good example to think about is for the primitive types, you'd be having strings, null, booleans, numbers, and then higher orders, things like binary expressions, which will be having a left expression, an operator, and a right expression. You'll be having things like unary expressions, and for the unary expressions, they take this just an expression, maybe which is the left or right value, and an operator that needs to work on it. So maybe it's a not operator or even increment, decrement, things like that. You might for the binary expressions, then of course you need to deal with things like plus, minus, divide, greater than, less than. So this way now it will be defining how those structures look like. And then in our parser, we'll now be trying to figure out what is the precedence for all these things. So we'll be able to structure them properly using the recursive descent parser. That's what we will be implementing today. And so at the end of today's video, we'll be able to show an AST. So later, we'll be adding a JSON library just to kind of use it to do some housekeeping. But first and foremost, let me first build some of these building blocks. So we need to build nodes, and these nodes are what now we shall be adding into our parser. At the root of them all, I will create a structure, a struct, and I will call it node. And this node, I'll have a string called name, and then I will have node type. I'll call it type. So I need to now define the node types I need to have, and I will call it a new class node type. And the first node type maybe I can have is called maybe program. The next one I can have is binary expression. So there are some primitive ones like string, literal, boolean, literal, and you also have number literals. So these are the primitive types. So at the core of every data we'll be handling, it will be these ones, and this I can just call them composites, or yeah. And then at the very end, we'll be having a okay, let me just put it that way. So I think we have captured most of the node types we need to work with. And okay. So let's include here so we'll be including string, and then so the name will just be basically the same to what we have here already, but in string format. Good. So this will be our root node. Another type of node we need to have now is what we call an expression. So I will come and do a struct, and this will be, it will extend a node, and for our expression, it will be the basis for all the expressions we'll be having. So today we'll be focusing so much on the derived classes from expression, not even node itself. But in the in future classes, in future videos, we'll look at how to add other complex things. We are not basically expressions, but they need to be part of this node structure. So here, let me add a constructor that takes node type of type T, and also takes a const of name, and so this will be that way. That's all what this node will be doing, and later we'll be adding some virtual methods that the derived classes need to implement. In our expression, I think I will also do a similar thing, only that now I will copy that and add it here. So this will be our constructor, which will just be taking that and it will be instantiating expression. It will be instantiating node. Yeah. So since expression is inheriting from node, so we need to pass up this data to the base class. So that's it about expression. So let's add some of the composite types. So I will come and do here struct. I'll call it binary expression. This inherits from expression, as of course, and then in our private members here, I need to have this way. We shall now be using pointers. So unique pointer of type node. I'll call it left, right, and then up. So for binary expressions, is basically you have a left value, an operator, and a right value. An example is doing 1 plus 1. You have left operand, the operator that needs to operate on two of them, and the right operand. So you have a binary expression. So left in this sense now is the left operand, right operand, and the operator which might be plus, minus, divide, multiply, whichever. So these are not necessarily need to be primitive types like 1, 2, 3, 4, 5. You might have maybe into bracket x plus 2 into bracket maybe there's an expression on the left and an expression on the right which needs to be evaluated. So for a constructor then in this case, our constructor needs to take std unique pointers of type node, and this is left, std string is up, and std unique pointer of type node. This will be the right value. This will be unique pointer. And then in our initializer list, we need to do left, and we'll move, since you're using unique pointers, we need to move the value passed in, same to right. And then for the operator as well, we can use std move up. One more thing to initialize is the expression, that's the base class. So I will do this, and inside here I will do node type, binary, and I will just do binary expression. So we can do formatting here a bit by taking these things to new lines. And then of course doing that. So for a binary expression, we'll be passing in the left expression, right expression, and the operand. So we'll be moving them into this class, and that's all about this node for now. The other node I need to add now is the primitive types. So let's do struct, and I will do number literal, and this inherits also from expression. I need a semicolon here. I'm missing a semicolon here. So this also, I think I will pass the value here. And then we'll build the rest. So let me first initialize the node type to be number literal. I'll just do number literal. And then I will also do here value to be value. For the number literal, which is still inherits from expression base class, we are creating it by passing in the value, and this value is in string format. So we'll be storing the string as it is, and then we shall be attempting to pass it into a double within the constructor. If it fails, we throw an error completely. So to do this, I will do this equals to std. I'll pass it the value. So this might throw an error, so if it happens, well and good, let it just fail. But it will be good practice to kind of plan ahead and capture that error and convert it as appropriately as needed. So for the number literal, that's enough for it. So I can copy that. Good. So we've done number literal, which is this. Let's also do Boolean. That way. And for Booleans, I think it will still be coming in as a string, so no problem, we'll be storing it as it is. But now the other, for let me just add here bool, and for Boolean we'll be storing it as let's do b value. Okay, so we'll initialize the b underscore value with value being equal to true. So if the value passed in is true, then it will be initialized to true, otherwise it will be assigned to false. And we'll still store the original string as it was. So, and then so you have number string, we have number, and then we have Boolean. So also need to capture in string literals here. So string literals. And for strings, there's no need for any kind of conversion, so you already capture it as it is. So string, so string literal is Boolean, this is number. Okay. And then lastly, we need to capture in the null literal. So no need to pass in any value. So the representation is already nil, so I'll just pass it as it is that way. And then I think I am missing one declaration here. Oh yeah. So we are missing the nil literal. So these are the primitive types: string, Boolean, number, and null values. So think that should cover it here. Yeah, so this also should be null. Okay. So I need a comma, semicolon as well here. So good. So those are all, okay, most of the expressions we'll be working with. So we have the string, null, Boolean, number, then you have the binary, and then we have expression, and then you have the node type. So that's mostly what you need for today's work purposely. So let's go back to Parser now. I think we already imported okay, so let's declare a class called node, and within our Parser class here, I will do a vector of std unique pointer of type node. Okay, let's import memory here. Include memory to get access to the std unique pointer. So I'm planning to store all the ASTs into this vector, but technically we don't even need a vector per se, because we can create a new class here, a new header I mean. It will be called struct, and this struct will be called program. Yeah, it will be called program. It inherits from node, and for program it will be having node type dot program, and this will just be the program. So this will be the root program node, and a private here I'll just do std unique pointer of type node. I'll call it root node. So what program will be doing is this will be the entry point to our AST, and I'll have a method here called void add node. Add node will be taking std unique pointer of type node, and what it should be doing is that maybe I should do here set node. So m root node goes to std move node. So we need to set the root node, that means the entry point of our program, and I'm using this. Okay, I might change my mind later, but let me keep it that way for now. And that means then I can, in my parser, I don't need a vector anymore. I can basically do here program. So we have our entry point, which is unique pointer of type node, and then we'll be assigning it to an expression somewhere. Now let's go back now to our parse method, because that's where now the bulk of the work needs to happen. We have declared node here. It's in the AST header file. In our parser.cpp, we have already imported here. We need to include, I keep saying import, I don't know if that's from JavaScript or somewhere. Includes expression evaluator, frontend, AST. So AST will now provide the node class in this particular instance. Now, when you call parse, let's first, because you have the lexer, we'll do lexer.tokenize and we'll pass here the source string. And of course, since this returns a token of strings, I don't have to worry much, because you'll be using the tokens method within the lexer class to access the generated token files. What I need to do here, of course, is to reset my cursor back to 0, and then I will do, so in our token class, I'll do while pick is not equal to token type EOF. Oh, this should be dot type, yeah. So as long as the current token we are checking is not equal to the end of file, so I think I named it program. I call it program. So I think I need to do here mprogram. Add node. So let me go back to my AST, and I think I'll revert this to unique, to vector. Let me just call it AST for now, and then we'll find a better naming later. So I think we also need to include here vector. So once you've included vector, and I believe binary numerical boolean string null, we are actually missing one more struct. I think let me fix that quick. And it's the identifier. So it will take the value. I think this as well should be identifier. Good. So I think I failed to add it initially inside the, yeah. So you should need to have ident literal. So it should be part of the primitive types. So it's part of it. So I think with that, identifier. Okay, good. So that means when you come back to the parser, we can do, so with the recursive descent parser, we need now to recursively call different methods depending on what we want to pass. So on the minimum side, let's pass expressions. And I think I didn't add the add, it was set. So let me confirm that the program node is now add node. Good. I need to fix my parser first. So there's no need to have a unique pointer here. We can just do program, and that means we need to include AST here. Yeah. So let me just, no need to grab. Okay. I can still do hash include AST, and that means this is no longer needed. And so program need a semicolon here at the end of the class. So our program is here. Now in our parser.cpp, our program will be .add node, and then we need to pass in the expression. So let's add these methods in our parser.h, and then we'll just come back to affix them where they're supposed to be. So in our private here, let's just make them public for now. So each of these methods will return a unique pointer, and it will be a unique pointer to type node. And the first one is parse expression. Good. So the next one will be parsing. So I'll put them in the order of how they should be appearing. So if you're parsing mathematical operations, then we need first to pass additives, that is addition and subtraction. So let me just call it additives. And then we need to pass what we call factors. So factors is multiplication, division, and modulus, those three. After factors, we need to pass, I think here would be primary. So I think that's what we need for use case right now. So if I come back to parser.cpp, for the parse expression, since we don't have much to do here, I will just return parse additives. So let's go straight into parsing, additions and subtractions. For additives, we need two things. We need the left expression and the right expression. So I will do here auto left, and for the left, we need to get we need to pass factors. So in short, we want to get any expression that has factors, if any. And then we need to have a while loop here, and this while loop needs to ensure that first of all, we are not at the end of file, and then two, as long as the current token, the current token we are looking at, dot type is equal to token type, and that's token addition or pick the type. So whether it's addition or subtraction, that's what you're basically doing here. And so for the order of operation, let's wrap this into that one. So as long as we have addition, so in case you have 1 plus 2 plus 3 plus 4, we'll collect all those additions and subtractions recursively. So we'll consume all of them. At the end of this function, we should return left. So this is the left, what you're doing here. And then inside this while loop, first and foremost, let's get the operator. So I will do std string up until be advance. So basically return the current token and advance the cursor, and then I will go here to value. So that will give me the current operator. And then we also need to make the right expression, so I will do that, and I will just also call pass factor, and that should return for us the right expression of this operand. And then once I'm here, I will reassign left, and here we'll do std make unique, and I'm making a unique of a binary expression. So remember, when you're doing, we'll make a binary expression unique, and then it expects the left operand, operator, and the right operand. And since you're using unique pointers, then we need to do std move of left. We'll do the operand, and then we will do std move for the right operand. So basically what is happening here, when you're passing additives, I will be calling these things recursively. So in the next step, we'll be calling the subsequent ones. So that basically means that the order of operations is that the last one in this call chain is the highest precedence. So, and that is things to do with unary, and then primary things like numbers, strings. Those are the highest precedence to be evaluated first. So those who are higher the chain have low precedence, and those who are lower, they have high precedence. So we are getting the left expression, and then we are collecting the operator we were dealing with. We also get the right one, and then we make a binary expression that has both this left and right inside it, and then this expression is returned as our left. So in case we have many chains, they'll be chained together, but we'll only return once here. So the same applies. So this same expression here applies also for this particular block, but the difference now being that in the pass factors, we'll not be calling pass factors, but we'll now be calling pass primary. So we'll be calling here pass primary. Similarly, we'll be calling here pass primary. Oh, this is supposed to be a function. And for this, as long as we are doing here multiplication, or we're doing division, so either of those two, we'll be able to collect it and call pass primary from there. Good. For pass primary, it's quite similar, but has some subtle changes. So for this, we'll use a switch, and we'll be switching on pick.type. Pick is a method. Now we'll do first case, token type. Let's begin with number. Okay. So first and foremost, let me just do let me call advance. So we'll consume that token, and then inside here we need to return std make unique, and what you're making unique here is a number literal, and this expects token.value as an argument. Let's for now, let's use the copy and paste just for, okay. And then we'll come here and do, for the next one, we'll do string literals. This will be a string. And then next will be a boolean. So this will be a boolean literal. And then we have numbers, strings, bool. We are missing null. Similarly, we'll be creating here an null literal, and this does not take in any arguments. So these are the AST classes we are making. So I think the remaining one here is token open parenthesis, and I think that will be the last one. So let me just put default here, and then we'll throw std runtime error std format unknown token let's do pick dot value. So if you reach this point, then there is nothing else to pass. We just throw this error. For open parent, then we need first of all to consume. We need to consume, so we don't need to pick that. So we need to consume. We need to consume the opening parenthesis token, and then next we need to get the left, and we'll do here parse expression. So within the parentheses, it might have its own expression which is complete. So let's pass the expression, and then after passing the expression, we need to get a closing parenthesis that matches what we are opening here. So we'll pass here expect, and in the expect method I will do, we are supposed to get token close parenthesis. For the error, I will do expected closing paren but was not found. So you can be very descriptive in terms of how you want to show these messages, but definitely if we reach this particular point, then we return left. Good. That means everything went well. So that's all about creating your AST tree. Now we need to visualize this AST tree to see actually the way we were showing this initially. And to do that, I'd love to use a JSON. I want to dump everything into a JSON. It's easier because JSON can be formatted to show some nice indentation. So what I'm gonna do, I'm gonna come to my browser and look for a JSON library called pico.json. I like it because I think it's a single header file that you can just copy into your. So we need this file, pico.json. It's close to, I think, 1200 lines, so I will copy it, come into my project here. I'll come to includes. I think here I will add the new file. Let me just call it pico.json as it is, and then I'll paste it as it is. So let me save it. Let me come back to my AST, and in my AST I will come to my node type here. I will add a new virtual method called to, let's call it dump. Okay, let me just call it dump. So this should return, okay, let me first include JSON library here. Okay. So each method will implement this, and this should be able to return. Let me implement for this. I'll just return. So we create an object. Then for the object, you have to define the fields you want to show. So pico.json value, and this value I'll pass it name, and this will be object. Good. So you create an object, and then you add the key value you want to have within the JSON object. Then you convert it to a pico.json value. Good. So this is what we'll need to implement for each of the nodes we have. Yes. That way we can visualize, we can dump them as need be. So let me come here. I'll put it here and then do here override. For this, the node type is program, of course, so there's nothing which changes for this. So technically there was no need to override that. So for node as well, no need to override. So where we need to override is from binary expression. And for this, we have the name, which is binary expression. And then we have object, then we have left, and for left we'll be doing so we'll be recursively for the operator. We'll be able to do just whatever already pick a JSON, and then also need to do for right. No, so for right we need just to recursively call dump. So whichever, if it's a number, literally it's a string, it will call the respective one because you're using the base pointer to call a derived class. And then once you're done, you just return the object. So let's come down to number literal. So we'll have the name, and then also we need to have the value. And here we'll have value. Okay, good. So for number, I believe that will be the same. For Boolean, we'll be doing b value here. So let's do the decimal equivalence. For the string, no need to change. And then for identifier, it will be similar to the string. So let me just indent these things properly. And then for null, nothing changes as well. Value will be nil. Yeah. So each of these nodes will be returning this kind of form. And then from our program, because our program is what is like the entry point to our AST, so our program also needs to override it, or basically have its own implementation. The name of course will be program, and then I think we need to do pick a JSON, array, and then I'll do array. And then for this, I will be doing for const auto a in MAST. So for each AST node in our array, let's append it by doing array dot pushback e dot dump. So in our ST Explorer, I think program, location, errors, comments, body. It's called body. So body is what they're using to refer to. So here we'll call it also body. And this will bear array. Then we'll return that. I think that will mark a good starting point. So we download this file. So remember, we need to clean most of these functions to move to the ast.cpp, but for now, let's try and visualize the work you have done. So the parser will have this, blah, blah, blah. So let's go to our parser.h, and then in our parser.h, also need to include picojson.h. In our parser.h, I will also do a similar method called dump. So I'll do picojson value dump, and then I will come to my parser.cpp. After the method pass, I will add it here, and then how to implement this, I'll just do mprogram. Oh yeah, I need to add here parser to know the context, and then I'll just do mprogram dot dump. So I will return this, and that's all we need to do here. So let's go up now to our main.cpp. Before we run this, we are importing our parser. From our parser, we need to do parser.pass, and you need to pass the inputs the user is keying in, and then from here, let's do parser.dump. So we need to dump, and I believe it should be true. Oh, no. I think this should be, okay, let me just first of all do auto D, and then we'll do std cout, serialize true. Good. So we'll not be showing the tokens per se. I think for now we are past showing tokens as well as the command. So hopefully this will run on our first try, but let's see. Why do I keep typing CLS? Okay, so let's fix the errors. So in our parser.cpp, format's not number std, so we need to include here format, and then same file. Error was not declared on line 30. Line 90. Okay. I think that should fix all the issues you have seen so far. Let's rebuild. Good, we are there. So let's do even 1 + 1. Good. So when you do 1 + 1 now, the main entry point is called program. That's what you had seen, and its body has, on the left part of it, has a number literal called 1, The type is a binary expression having the left of that. The operator is plus, and the right is a number literal of 1 as well. So if you do x plus 2 into 4 divided by 3, oh yes. So we later added identifiers into the AST, but we failed to tell our parser how to parse identifiers. So if you come to our primary, so you need to I think here we need to do identifiers. Yeah, that's actually defined. So what is the issue here? I don't know why I don't see an. Let me just rebuild it. Identifier. Argument 1 is invalid. Identifier expects a string for the identifier name. Which is fine. I think I did a typo here, so that's why I'm wondering why. It should be identifier, not identifier, and that should be fixed. Good. Let's say run that. So if we now do 1 plus 2 divided by 3 times 5 minus 2. So this will now build a very nice AST, whereby if you look at the order of operations, whatever is within the brackets needs to be evaluated first. So 3 times 5 minus 2, we need to do 3 times 5 first before we do minus 2. So we need to do 3 times 5, and then once you're outside this block of left, we now do minus 2. And then all that will now be added now to, we'll first do 2 divided by the answer, and then we add 1. So this shows you how to structure your full program, and in terms of an AST. So this is an AST tree, similar to what you are seeing when you're looking at this one, but this is more detailed because it comes even with the location for your particular tokens. So these are things you can basically add later to show you some of those functionality. So with this, I hope you found this segment a bit more, entertaining and interesting to think and work around some of the challenges. what remains now is to basically piece everything together and build an interpreter which will be able to evaluate what you have done so far and give us an answer. So instead of spitting out all this AST, we'll be able just to evaluate this AST itself and return the resultant value. That's what we'll be doing in our next video. So stick around and I will see you in the next video. Bye.